Good day everyone. Today we are going to discuss about the MRI basic physics. What do you mean by MRI? MRI is nothing but stands for magnetic resonant imaging. We are going to see the three components of MRI, that is magnetic resonant imaging. This video consists of three components of MRI. First, before we are going to deal with what is MRI, human body is made up of 62% of water. 62% of water and 16% of fat. These both water and fat is made up of water and fat made up of hydrogen atoms. Hydrogen atoms. These hydrogen atoms, let us consider H2O. H2O, when it reacts, it produces 2H plus and O2 minus. So what it means is the hydrogen atom contains one proton and one electron. This electron will be given to the oxygen molecule. In fact, we can see hydrocarbons. Here, the hydrogen will give its electrons to the carbons. So it will become H plus. So all H plus indirectly means it has only one proton. Only one proton. That's what we called as H plus is otherwise known as proton. Proton. What do you mean by proton? The H plus, otherwise known as proton. This proton has an intrinsic characteristics what we called as gyromagnetic property. This gyromagnetic property is nothing but it can spin on its own axis. It can spin on its own axis. This is the property we are going to use in our MRI imaging. MRI imaging is nothing but we are imaging the proton or hydrogen H plus in our human body. Now first component, magnetic component. We know that the MRI machine has many magnets. First we have primary magnet. Today we are going to discuss about only the primary magnet. Then we have gradient coils and radiofrequency coils, etc. What do you mean by primary magnet? What it does? The primary magnet will produce a magnetic field in the center of the bore. In the center of the bore. Here we can see the magnetic field which will be produced will be aligned in the center of the magnetic field along the direction of the center. Here we can see human body is placed within the center of the MRI machine. We can see the direction of the magnetic field is along the center of the bore. That's what we called as B0 because of this primary magnet. Primary magnet. We have already mentioned that the human body is consist of H plus. Plenty of H plus. This has its own magnetic momentum. That's what we called as magnetic momentum. That's gyromagnetic property. It wobble on its own axis. Because of this B0, it affects these small magnets, small H plus magnets, and it will be aligned along the axis of the B0. Here we can see the human body consists of multiple atoms, multiple H plus, which are wobbling on its own axis in different direction. The net magnetization vector is 0. Here the net magnetization vector is 0. Whereas once we are placing the human in the center of the magnetic bore, we can see the B0, the primary magnetic field B0 is going to impact on each magnet, small magnets, that is H plus ions, that protons, and it will try to pull along its axis. And we can see here all magnets, all small magnets in our body, that all protons, all H plus atoms are seen along the direction of the Z axis. This is the first process which is going to happen on the MRI. That's the M component. Magnet component will cause alignment of the H plus ions along its axis. This is the first component. What other thing it does? We know that H plus ions are rotating on its own axis. H plus ion are rotating on its own axis in random direction. Once we keep the patient or human body within the center of the MRI machine, it does two processes. One process we have discussed already, it aligns along its own axis. Second process, it increases the spin of the H plus ions and it causes some wobbling motion. That wobbling motion is what we call as precession frequency. Precession frequency is nothing but whenever a hydrogen atom is kept within the MRI machine, it will cause increases in the frequency of wobbling, and it wobbles on its axis, what we call as precession. This precession frequency is very important. Let us consider if we have 1 Tesla machine. In 1 Tesla machine, the precession frequency will be around 42.5. Whereas in 2 Tesla machine, it will be around 63.5. How does it comes? It's given by a equation what we call as Larmor frequency. What do you mean by Larmor frequency? Here we can see omega naught is equal to gamma B0. This B0 is the main magnetic field, primary magnetic field. And omega 0 is the precession frequency. That is, whenever we kept an H plus ion within the magnet, center of the magnet, it will increase the frequency of rotation. This is given by an equation called omega 0 is the precession frequency is directly proportional to the B0. The precession frequency of the H plus ion is directly proportional to the magnetic field. If the magnetic field strength is increased, the precession frequency of the H plus ion going to be increased. So to remove the proportionality, we are going to introduce a constant. That's what we called as gamma B0. This gamma B0 constant stands for gyromagnetic ratio. That we have discussed already, gyromagnetic ratio. This gyromagnetic ratio value will be around 42.5. Let us consider B0, the main primary magnetic field, which is produced by a 1 Tesla machine, MRI machine. Then the precession frequency of the H plus ion will be 42.5 into 1, that is equal to 42.5. Whereas if we are using a 2 Tesla machine, 1.5 Tesla machine, 42.5 into 1.5 is equal to 63.5. So this is the precision frequency of the H plus ion within the 1.5 Tesla machine. Okay. What is the importance of this precision frequency? Why it's important? Before knowing importance of the precision frequency, we need to know the term resonance frequency. What do you mean by resonance? Resonant frequency is nothing but whenever we have to give some energy to the H plus ions which is aligned along the main magnetic field, it has to be similar to the precision frequency. If let us take an example. If in 1.5 Tesla machine, the precision frequency of H plus ion is around 63.5. The H plus ion precision frequency will be 63.5. It's in the direction of the main magnetic field. It's in the direction of the main magnetic field. That is Z0, Z axis. This is the net magnetization vector. Net magnetization vector is along the Z axis. Now, if we have to change the direction of these three H plus ions which is along the Z axis to Y axis, we have to give a frequency or energy. It should be similar to 63.5. The RF pulse must be 63.5. Then only it can take up the energy and it changes direction from longitudinal direction to transverse direction. This net magnetization vector is along the longitudinal magnetization to transverse magnetization. We need an energy similar to that of the precision frequency. Then only it can be changed to the another direction. That's what we called as the precision rate. The frequency of the precision rate must be similar to the RF pulse which we are going to give. Then only the magnetic direction, the magnetic direction will be changed from longitudinal magnetization to transverse magnetization. See here we can see the example, the RF pulse which we are giving, a 90-degree RF pulse we are giving. The magnets is along the net magnetization as along the longitudinal direction. We are giving the precision frequency is around 63.5. At the same frequency we are giving an RF pulse. It changes its direction from longitudinal to transverse. Longitudinal to transverse. Here we have an example. Another example. Here we can see all magnets which is along the Z axis. That's what we called as longitudinal magnetization. Now we are giving an RF pulse with the same frequency. It converts from longitudinal to transverse magnetization. Here we can see longitudinal to transform to longitudinal magnetization to transverse magnetization. Here the net magnetization vector is along the transverse magnetization. There is no longitudinal magnetization in this direction. Now what we are going to do is, we have completed the second component, resonance. Next we have third component, image formation. How we are going to form the image. Now what we are going to do, we know that it's in the vector is along the transverse magnetization. Now we are going to switch off the RF pulse. The RF pulse which we have given before, it's switched off. Now what happens? Because of B0 is along the longitudinal magnetization, it pulls back all the hydrogen atoms which are persisting in transverse magnetization towards the longitudinal magnetization. So there is an increase in longitudinal magnetization. During transforming back from transverse magnetization, it loses its energy. This energy is converted as an It energy is captured by an receiver coil and it's transformed as an echo. The echoes which are produced by all hydrogen atoms are transferred to an K space. Here we can see multiple lines. This is what we call as K space. After filling all this K space, it is undergoes an Fourier transformation, then image is produced. Summary of this class. We know that human body is made up of hydrogen atoms. MRI is nothing but imaging and hydrogen protons. So we have multiple molecules H2O. Here once we have only H plus, it will has its own magnetic momentum. That's what we call as gyromagnetic property or ratio. Here it's in random direction without magnetic field. Once we are entering into the MRI machine, it aligns along the direction of the magnetic field, primary magnetic field, that's B0, along the Z axis. So net magnetization vector will be longitudinal magnetization vector. Once with the same precision frequency, we are going to give the RF pulse. This RF pulse will cause from transverse to longitudinal to transverse magnetization. Once we stop the RF pulse, it will recover. While recovering, it will produce an echo. This echo will be transferred into an K space. Then this K space will be converted into an image, MRI image. Thank you for your patient listening. Please share, like and comment. Thank you.